Can you hear me? Hello.
Yes, sir.
Am I audible? Okay. Am I audible to everyone?
Yes, sir.
Okay. So
Yes, yes.
let us take 2-3 minutes and then we can join. Okay. So wait for 1 or 2 minutes. Once the sufficient students are there, we will start. Okay. Now it is just 104. Okay, so can we start? Hello, hello. Am I
Yes,
audible
sir.
to everyone? Okay, so please pay attention. Let me include if some students are there.
मेरे पास थी ना 3
तीन थी।
1 थी।
एक जगह गया था मैं किससे कल।
Okay,
सही किया।
ले गया था। फिर तेरे पे किससे।
is my slides visible to everyone? Hello.
यस सर, यस सर।
Okay, so let me start from the. Okay, so in the last class today, we started looking at root locus, and then we have seen 6 rules given by Evans, and based on these rules, we have also looked at how we can draw the root locus for 2 case studies, isn't it? One with proportional controller and another one with PI controller, isn't it? How the root locus is going to vary and how we can uh, draw a rough sketch of root locus, and then we can refine the root locus based on the angle criteria and magnitude criteria. That is what we have discussed in today's class. What we are going to see today in this particular class is we are going to look at frequency response analysis of the linear processes. Before we start the frequency response analysis of the linear processes, let me ask this question: why frequency response? Okay, so see, remember how this course started. Initially we had this first question in our first class was why process control, isn't it? We said process control is required because there will be continuous input of the disturbances in the system, and we wanted to negate the impact of these disturbances on the uh, response, isn't it? My control variable should not vary even if there is a disturbance coming in continuously in the process, isn't it? That was one reason. Another reason was to make the inherently unstable process stable, and the third reason was uh, to optimize the process, isn't it? So these are the 3 reasons for which the process control is required. Then we have seen several components of the required for process control. So we started with modeling, isn't it? We said we can do the control of the process only when we know the process well, and knowing the process well means what? Either we can perform the experiments or we can model the system in terms of equations, and then we can obtain the state of the system at any time and at any location by solving those equations, isn't it? So knowing the system is nothing but formulating the model. Then we said, okay, the model is formulated, how we can deal with this model? So for that, then we said, okay, we are now restricting our analysis only to linear process control. And in a linear process control, we will have a linear differential equations mostly. So in order to deal with this linear coupled differential equation, if we use Laplace transform, then the linear coupled differential equation will give me linear algebraic equations, and we can solve these linear algebraic equations easily, and we can find out the state of the system easily, isn't it? That's what we started. Then we said, okay, this is all right. We started looking at the components like modeling and Laplace transform. Now let's look at how this particular information we can use in control, isn't it? So there came the concept of feedback control system. There came the concept of stability, isn't it? Correct. So this is what we have seen over the period. All right, isn't it? Does it make sense what I'm saying to everyone?
यस सर।
Hello.
Yes, sir.
So in the stability also, see, when we seen the feedback control system, in feedback control system we said uh, the feedback control system, since the controller is there and controller will have its own parameters which the user has to specify inside, isn't it? So value of kc, value of tau I, value of tau d, these are the parameters the user has to specify, and depending on what value the user is putting in this controller parameter, your system can be stable, unstable, your system can be oscillatory or non-oscillatory, isn't it? Or based on that, depending on where the roots of the characteristic equation are, your uh, the qualitative nature of your response you can predict, isn't it? So for that we started looking at Raoult stability criteria. In the Raoult stability criteria, we said we can find out the stability of the control system without finding the roots. That was the argument we gave, isn't it? Whenever I wanted to find out the stability of the control system, I can just solve 1 plus open loop transfer function equals to 0, and I can find out uh, the uh, the polynomial in S. And then based on this polynomial in S, I can use the Raoult stability criteria, and I can find out whether a given control system is stable or not, isn't it? Very, very easy. But then another argument we gave, saying that we can find out the stability of the control system without finding the roots, but still we need to know the location of the roots. Why? Because what type of response I'm going to get, whether it is oscillatory, whether it is non-oscillatory, this information we can get only by finding the roots, isn't it? And there came root locus, isn't it? So even though we started with Raoult stability criteria, but then we have to still move to the root locus, primarily because uh, the response, what type of response I'm going to have, is actually dependent on where the roots are located, isn't it? So more than stability, also what will be the nature of response, that is also important, isn't it? So that is the reason why root locus came into the picture. Now the question here is, we should have stopped the process control there itself, isn't it? We started with modeling, we started with why process control is required, then modeling, then Laplace transform, then feedback control system, and then stability of the control system. This is what we have seen so far, isn't it? But then why we have not stopped at root locus? Why we are extending our analysis to frequency response? This is the question. Did you get my question? Why I'm asking this question? We should have stopped our process control just before the frequency response. Why we are at all studying the frequency response? What is the reason? Anybody? Why frequency response is actually part of your syllabus? Should we eliminate this from your syllabus? Okay, because everything, all the components required in process control we have already studied, isn't it? Why process control, then modeling, then how we can analyze the results using Laplace transform, then feedback control system, and finally the stability of the control system. All the aspects we have studied. Then why we are looking at frequency response? What is the need of the frequency response? Is the question clear to everyone? Hello?
Yes, sir. Yes, sir.
No, but only one student is saying. I am asking all the students, please say, because I'm
Yes,
only seeing
sir.
the screen. Okay.
Yes, sir.
So what is
Yes,
the
sir.
reason why process frequency response is at all a part of process control? Why we have not stopped our syllabus
Sir,
just before frequency response? Please go ahead.
sir, sir, if the input of a system follows the that oscillatory input, then we will need this frequency response system.
No, that is not the reason. That is not the reason. Oscillatory response we were anyway looking at earlier also, isn't it? Depending on the location of the roots, we can find out whether the response is going to be oscillatory or non-oscillatory, isn't it? Isn't it? Correct? Correct or not? Let's say here I am looking at the root locus. If my roots are complex, in that case, I'm going to get the oscillatory response. Done. That part anyway we have covered in root locus. Then what is the reason of using the frequency response? Anyone? Any other reason? If the frequency response is a part of your syllabus, there should be some solid reason for that, isn't it? It's not just for the sake of making mathematically things complicated, isn't it? Anyone? What could be the reason why frequency response is? First of all, what is frequency response? Frequency response is nothing but if you give a sinusoidal input to the system, how my system is going to behave. Analysis of that is referred as frequency response. Okay. Now, why we dealing with frequency response at all in this course. Any
Sir,
other
till
good
now,
reason? Ha, please go ahead.
sir, till now we are giving not a sinusoidal input up to like a
So
control
then I
system.
will ask, my counter question is, why sinusoidal input we are using? Do you think the real life input will be a sinusoidal input? Real life, the input will be, random. Hardly it will be sinusoidal, isn't it? Sinusoidal input is usually a tailor-made input, isn't it? Usually a sinusoidal input is a tailor-made input. Yes or no? But why we
Sir,
are,
if
studying
input
this?
is,
Uh,
for example, if input is, we say electricity or voltage, then it will follow that sinusoidal type input, I think.
no, 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 no. And where the input is, okay, input to the process, let's say reactor you are looking at, flow rate coming to the reactor, do you think it's an electrical signal? It's a
Sir,
material
in
flow.
case,
It's a
if
material flow,
it is electric
correct?
signal,
Huh?
in case if it is electric signal, that it will follow the
So
sinusoidal input
I
of
am
50
giving you a
hertz.
real life example. There is a reactor. In this reactor, the input is the flow rate. Outlet is again outlet flow rate. So that is not coming from any electric signal. The input is input flow rate. Okay. It will not be a sinusoidal, isn't it? This course is process transfer, process control, isn't it? It's not control system. Control system is a part of electrical engineering. There somebody is saying this, then okay, that could be one reason. But in a process control, most of the time we are dealing with process system like reactors, distillation columns, etc., isn't it? So where this sinusoidal uh, input and its analysis is important. Why it is important? Any other student? Okay, so let me give you the answer for this question. This is a very, very important question. Why I am saying, because most of the time, wherever the process control is taught, typically this particular question remains unanswered. People teach a frequency response, but they will never, explain you why frequency response. Hmm. The reason for frequency response is date time. Okay, I will, as we go ahead, you will see why frequency response is relevant here. So whenever a process is associated with a date time, then the stability of the control system you can find out without approximating the date time only by frequency response. And every system you look at, there will be always a date time associated with that. There will not be any system without a date time. Date time is always associated with the system, isn't it? So whenever I am having a system with date time and I wanted to find out the stability of the control system, if I am using a route stability criteria or a root locus, for instance, in this case, let's say, okay, let me take example here to explain the concept. Okay, so here you can see that the GP is given as 1 upon tau 1 s plus 1 into tau 2 s plus 1, isn't it? This is the GP. Let's say I am saying that this process has a date time associated with it. So what will be the transfer function typically? What will be the transfer function? You will have a exponential term e raised to the power minus TDS. Yes or no? In the transfer function. Correct or not?
Yes, sir.
Hello?
Yes,
So
sir.
Yes.
if I am having a e raised to the power minus TDS, what will be the characteristic equation? 1 plus k into e raised to the power minus TDS divided by s plus 1, s plus 2, s plus 3. Now exponential term is there in this characteristic equation. How I can solve this particular characteristic equation? There is one way of doing it. That way is you can approximate this e raised to the power minus TDS by a Paird's approximation, isn't it? You can approximate that by using a Paird's approximation and then solve it. But Paird's approximation, as the name itself suggests, it's an approximation. That means whatever the solution you are going to get will be a approximate solution. Okay. So whether you use a root locus or a route stability criteria, whenever there is a exponential term present in your transfer function, you can approximate that exponential term by using Paird's approximation. But then whatever the results you are getting will be approximate results. Okay. And date time is so commonly present in all the process that you will not be able to have any process without date time. Every process will have some date time, isn't it? Correct. Now the question here is, can I find out the stability of the control system without approximating the date time? You can find out the stability of the control system without approximating the date time only by using frequency response. And that is the reason why frequency response is a part of your syllabus. It's not, it's not to make your life, miserable in terms of mathematics. No, that is not the reason. The reason, prime reason for involving the frequency response in your syllabus is the system with date time can be analyzed for stability without approximating the date time, only using frequency response, only using frequency response. And that is the reason why frequency response is a part of your syllabus. Is that clear to everyone? Is that clear to everyone?
Yes, sir.
Hello. Now this
Yes,
argument I
yes,
am
sir.
going to prove. I am going to prove this argument. Okay. Now so far we have not seen any proof why I am saying that date time can be uh, date time can be analyzed without approximating it using a Paird's approximation by using frequency response. This particular argument I am going to prove. Okay. Okay, let us start with a very simple system. Let us start with a first order system. So this is the typical transfer function of the process, which is Kp divided by tau ps plus 1, isn't it? And let's say that there is a input to this process. Let's say ys is the output and input here is f of s. Let's say f of s is a sinusoidal input which is given as a sine omega t, where omega is the frequency. Okay. This particular proof we have seen earlier, but there I have given directly the final expression. But now you can see the detailed proof of this particular input for a first order system. So a sine omega t, I can obtain f of s. I can obtain the Laplace transform of this input. So that will be given by a omega divided by s square plus omega square. And if I multiply this f of s here, what I'm going to get is ys will be given as kp divided by tau ps plus 1 into a omega divided by s square plus omega square. Now in this particular equation, I wanted to find out yt. So I have to invert this entire equation to a time domain. How I can do that? I have to separate the partial fractions and then invert individual partial fractions into a time domain, isn't it? So in this case, I can divide this equation by tau p. So what I'm going to get? I'm going to get kp by tau p divided by s plus 1 by tau p into a omega divided by s square plus omega square. So again, this entire equation I am representing in terms of three roots, isn't it? Three roots of the denominator. So first root will be minus 1 by tau p, second root will be minus j omega, and third root will be plus j omega. So c1 divided by s plus 1 by tau p plus c2 divided by s plus j omega plus c3 divided by s minus j omega. In this manner, I have separated the partial fraction. And now I am actually finding out this constant c1, c2 and c3. What is the procedure? I have to multiply this entire equation by s plus 1 by tau p and then put s equals to minus 1 by tau p, and that will give me c1. So that's what we have done. We have multiplied this s plus 1 by tau p to both the sides, left hand side and right hand side. With that, what will happen? This s plus 1 by tau p will get cancelled out, isn't it? So only thing remaining on the left hand side will be kp by tau p divided by a omega divided by s square plus omega square. And then we have to put s equals to minus 1 by tau p. So if we put that in terms of s, we can put minus 1 by tau p. So this is what we are going to get as a c1. So c1 comes out to be directly kp a omega tau p divided by 1 plus tau p square omega square. So c1 we have obtained. Similarly for c2, again we can multiply this equation number 3 by s plus j omega and then put s equals to minus j omega. So with that what we are going to get is this s will be replaced by minus j omega, isn't it? minus j omega, and this s will be represented by again minus j omega, so that will become minus 2 j omega, and here minus j omega. So again we can simplify this. After simplification, what we are going to get is kpa divided by minus 2 omega tau p plus iota. Now here the iota is in the denominator, so whenever we have a iota in the denominator, what we do, we multiply and divide a particular term so that this iota we can eliminate, isn't it? So in this case again we can multiply and divide by omega tau p minus iota. If we do that, what we are going to get, we are going to get kpa omega tau p minus iota divided by minus 2 tau p square omega square plus 1, and that will be the constant c2. Is it clear to everyone, this part? Hello?
Yes, sir.
Similarly, we can find out c3. C3, in order to find out C3, again we can multiply this equation number 3 by S minus J omega, and then we can put S equals to J omega. With that, again we can find out C3. So C3 comes out to be KPA divided by 2 minus omega tau p plus iota. Again here the iota is in the denominator, so we can multiply and divide this entire equation by omega tau p plus J. So with that we are going to get KPA omega tau p plus iota divided by minus 2 tau p square omega square plus 1. Okay, so we have obtained c1, c2, c3, all three constants we have obtained. We can put those constants here, and we can invert this entire equation into a time domain. Okay, so this is the equation we have obtained. Now in this particular case, let's concentrate on these last two terms. So these last two terms are what? If I invert this entire equation into a time domain, what I'm going to get? I'm going to get yt will be given as c1 e raised to the power minus t by tau p. What will be the inverse Laplace transform of this? That will be C2 e raised to the power minus j omega t. And this last term is going to give me C3 e raised to the power plus j omega t. Now let's concentrate only on these last two terms. So these last two terms are C2 e raised to the power minus j omega t plus C3 e raised to the power j omega t. Now put C1, C2 and C3 here. So if we put C2 and C3, these are the terms which we have put. So in this case, C2 is given as kpa omega tau p minus iota divided by minus 2 into tau p square omega square plus 1. So this tau p square omega square plus 1 upon tau p square omega square plus 1, this entire term we have taken common. And again, e raised to the power minus j omega t, this is represented in terms of sine and cos. So this e raised to the power minus j omega t is given as cos omega t minus j sin omega t. Similarly, we can put C3. So C3, again this common denominator is taken out. So with that, the remaining term here is kpa omega tau p plus iota divided by minus 2. And again this e raised to the power j omega t is represented in terms of cos and sine. So that is given as cos omega t plus j sin omega t. Now we can rearrange all the terms. After rearranging all these terms, what we get is kpa tau p omega into cos omega t minus kpa into sin omega t divided by tau p square omega square plus 1. Okay, so I can separate these terms here. So ultimately, if we put those all the terms here, what we get is kp omega tau p divided by tau p square omega square plus 1 e raised to the power minus t by tau p. This second term, this minus kp a omega tau p is there, so that is written here minus kp a omega tau p divided by this common denominator, which is tau p square omega square plus 1 cos omega t, and this minus sign multiplied to this minus sign, that becomes plus. So the remaining term here will be kpa divided by tau p square omega square plus 1 sin omega t. Again, this cos omega t and sin omega t, these two terms we can combine, isn't it? Further, if we find out what will be the response at t tends to infinity, that means we are interested in finding the steady state response. In that case, e raised to the power minus t by tau p, this particular term is going to become 0, isn't it? Because tau p is a positive number, minus t by tau p, that this entire term is going to be becoming 0 as t tends to infinity, isn't it? So when t tends to infinity, this entire term becomes 0, and I can combine these remaining two terms using this particular formula. So a1 cos b plus a2 sin b will be given as a3 sin b plus 5, where a3 is given as under root a1 square plus a2 square, and 5 will be given as tan inverse of a1 by a2, isn't it? So that's what we have done here. isn't it? So with that, the steady state value of this yt is given as kpa divided by under root tau p square omega square plus 1 sine omega t plus phi, where phi is given as tan inverse of minus omega t. So this entire derivation we have done from the scratch. Remember when we have started initially, this I have given this last term directly. I have not derived at that time one by one. Okay, is it clear? This entire derivation is not there in your book. This detailed derivation is not there in your book. Okay, in your book only this final expression is given. Is it clear to everyone?
Yes, sir.
Hello. Okay, so now what we are concluding here? What we are concluding? If you look at this response, YSST is nothing but what? It is nothing but the steady state response of the uh, process when t tends to infinity, isn't it? So the steady state response is given as kpa divided by under root tau p square omega square plus 1 sine omega t plus phi, isn't it? What was the input to the system? The input to the system was a sine omega t. Correct? That was the input. So what we can conclude here? The input was sinusoidal. My steady state output is also a sinusoidal, isn't it? The only difference here is my output will have a amplitude of kpa divided by under root tau p square omega square plus 1. That will be the amplitude of the output. And further, this output will be lagging behind with a phase angle of phi. Why I am saying that this is a phase lag? Because phi is going to be tan inverse of minus omega tau p. This minus sign is there. That's why I'm calling this phi as a phase lag. Minus sign is there. Okay. So you can see that my output is lagging behind my input with a phase angle of phi. However, my output will be a sinusoidal wave with a frequency omega, but amplitude will be kpa divided by under root tau p square omega square plus 1. And you can see that the amplitude here depending, so see input will have an amplitude of a, but output will have an amplitude of kpa divided by under root tau p square omega square plus 1. Is that clear to everyone?
Yes, sir.
So the conclusion here is the ultimate response, also referred as a steady state response of a first order system to a sinusoidal input, is also a sinusoidal wave with the same frequency omega. Again, if we calculate the ratio of the amplitudes, ratio of the amplitude of output and the input, that particular term is referred as amplitude ratio. So amplitude ratio comes out to be kp divided by under root tau p square omega square plus 1. Okay. भैया क्या हो गया? म्यूट कर लो यार. Okay, so amplitude ratio will be given by kp divided by under root tau p square omega square plus 1. Okay, and the phase lag in this case will be given by tan inverse of minus omega tau. Now the important conclusion we can draw here is, this is for a first order system. For a first order system, the conclusion is my steady state output will also be a sinusoidal wave with a frequency of omega same as the input, and the amplitude ratio is given as kp divided by under root tau p square omega square plus 1, and the phase angle will be given by tan inverse of minus omega tau p. Now these three observations are not only true for the first order systems but also for any of the linear system, any order linear system. You can see that a similar type of results you are going to get, and we are going to prove this generalization. Okay, so this sinusoidal input to the first order process, we have seen the analysis. Now we are going to see a generalized analysis, and then we can conclude that whatever the conclusion we are having here, similar conclusions we can get even for a general system, general linear multi-capacity processes. If you see, you will get a similar conclusion there. Okay, that is what we are going to prove. Before that, let's look at some basics. Remember, when we have started looking at the proof of the second order system and its amplitude ratio and phase angle, that was the tutorial number 6, if I am not wrong. there we have used one property. Remember, the property was, whenever a complex number is there, the complex number can be represented in terms of its magnitude and phase angle. Correct? That was the property we have used. We are going to prove that property here. Okay, so let's see here. There is a sinusoidal input which is given by a dotted line. Dotted line is the input. Okay, and the output is shown by a solid line. You can see that your output will be lagging behind your input, and that is why, if you look at the difference between these two peaks, that is given as phase shift. You can see between input and output there is a phase shift, which is nothing but phase angle phi. Also, if you look at the amplitude, so the amplitude of the input is A, whereas the amplitude of output will be given by what? Amplitude of the output will be given by A into amplitude ratio, isn't it? A into amplitude ratio will be given as your amplitude of your output. Typically, the amplitude of the output is lower than the amplitude of the input. That is what we see. Okay. Is this graphical representation clear to everyone? If something is not clear, please ask me, because this chapter is extremely important. If you don't ask me, if you don't get something, then we will have a difficult time. Okay. So please ask me if something is not clear till this point. Is it clear to everyone?
Yes, sir.
Yes, please ask. Somebody was asking the question. Is there a question? Hello?
No, sir.
Okay. Okay. Now let's look at the property. Remember, I said any complex function can be represented in terms of its magnitude and its phase angle. Let's take a complex function W, which is represented as A plus JB, where W is given as A plus iota beta, where A is a real part and B is a imaginary part. Okay. So in this case, A is given as real part of the W, whereas B is nothing but imaginary part of the W, isn't it? Correct. Now, if I wanted to find out the magnitude of this particular complex function W, what will be the magnitude? Magnitude will be nothing but what? Under root of square of the real part plus square of the imaginary part. Do you all agree with me?
Yes, sir.
Is it clear to everyone? The modulus or the absolute or a magnitude of W, which is a complex function, will be given by mod of W, and that is given as under root of square of real part plus square of imaginary part, isn't it? Correct? Yes or no? And similarly, the phase angle between the real and the imaginary part will be given by what? It will be given by argument of W, and that is given as tan inverse of imaginary part by real part. So tan inverse of imaginary part by real part is going to give me the phase angle theta. So are you all with me till this point? This you might have done in your school days, but still, are you all with me? Hello?
Yes.
Can we go ahead? Hello? Can we go ahead? Please respond. Can we go ahead? If only one student is speaking, I feel as if I am, speaking to the screen. So you have to make the online classes little bit more lively, because I'm not able to see you. Okay. So can we go ahead? Are you all with me?
Yes, sir.
Yes, sir. Yes.
Okay. All right. Okay. Now let's look at this particular function omega a little bit in more detail. So remember, I said A is a real part and B is a imaginary part. If I represent this particular function W in a complex plane, I can represent the imaginary part on the y-axis and I can represent the real part on a x-axis like this, isn't it? Correct? where the length of this W, length of this particular point from the origin will be nothing but its magnitude. Do you all agree?
Yes. Yes.
Now, what will be A? What will be A? A will be nothing but what? This magnitude here, which is W. W into cos theta. W into cos theta will give me A. Do you all agree? Magnitude W into cos theta will be A. Yes or no? See, remember I am saying that the length of this particular point from origin will be nothing but the magnitude. So magnitude is nothing but what? It's nothing but the mod of W, isn't it? So this particular length is going to give me the modulus W, isn't it? So what will be A? A will be modulus W into cos theta, where theta is the angle between the real axis, isn't it? Correct? Do you all agree?
Yes, sir. Yes, sir.
Similarly, what will be B? B will be nothing but modulus of W into sine theta. B will be the modulus of W into sine theta, because this is the length I am looking at. B. Correct? This is the length I am looking at. So now in this case, A plus J beta is what we have represented W. So now A is W modulus W cos theta, B is modulus W sine theta, and I can add in this equation. So what we will get? Modulus W cos theta plus J modulus W sine theta, that should be equals to W, isn't it? Now cos theta is represented by what? Cos theta is represented by e raised to the power j theta plus e raised to the power minus j theta divided by 2. And similarly, sine theta is represented by e raised to the power j theta minus e raised to the power minus j theta divided by 2 iota. If I put this sine theta and cos theta in this particular equation, this is what the equation I'm expected to get. Now this iota will get cancelled out with this iota, and this omega modulus I can take it common, isn't it? And if I collect the other remaining term, what I'm going to get? I'm going to get modulus omega into e raised to the power j theta. So we have proven what we have proven here. Any complex number can be represented in terms of its modulus and its phase angle using this equation. Do you all agree?
Yes, sir.
This is what one of the question one student has asked me in the tutorial. Remember? So this is the proof. Any complex function can be represented in terms of its magnitude, which is nothing but the modulus of W, into e raised to the power j theta, where theta is nothing but the phase angle. Okay. All right. Is it clear to
Yes, sir.
everyone?
Yes, sir.
Now, let's say I am having another complex function which is given as a minus j beta. The only difference is here the plus j beta, jb is there. Here a minus jb is there. So minus iota b is there. Correct. Now, in this case, if I find out the magnitude of this z, what will be the magnitude of this z? Under root of a square plus under root of minus j square. So minus j square will be just j square. So modulus of z will be same as modulus of w. Do you all agree?
Yes.
But when you are comparing the phase angle, what happens to the phase angle? Phase angle, I will have a minus sign here, isn't it? When I'm looking at the phase angle of this, I will have modulus of w into e raised to the power minus j theta I'm going to have. So clearly the argument of z should be equals to minus of argument of w. Do you all agree? So phase angle will be minus sign here. Do you all agree?
Yes.
Okay. Now once these basics are done, now the question here is how we can use these basics intelligently to obtain the frequency response. Just a minute. How we can use these basics to obtain the frequency response? That is what the question we are trying to answer. Can anybody say? Can anybody say how we can use? Remember when we have started looking at the derivation earlier in the starting initial classes, I said that I said that this proof we have seen, first order process with a sinusoidal input, a detailed complex proof we have seen. In fact, we don't need to have such a complex proof. Instead of having such a complex proof, we can obtain the final answer directly without doing the complex proof. That is what I said. And I said at that time that this particular procedure we are going to look at later on when we will look at the frequency response. Do you all able to remember? Hello? Are you able to remember what I'm saying? I am saying
Yes.
that remember this complicated proof we have obtained. Remember this entire complicated proof we have done, isn't it? And finally, we have obtained this equation. YSS is given as KPA under root tau p square omega square plus 1 into sine omega t plus phi. And I am saying that in order to obtain this proof, I don't need to go through this entire detailed procedure which I have shown here. In fact, I can get this final answer directly. There is a trick to get this final answer directly. And what is that trick? The trick here is whenever you are having a linear stable system, you just replace s by j omega in the transfer function. You can replace just s by j omega in the transfer function and then find out the phase angle and the magnitude. So magnitude will represent the amplitude ratio, whereas the phase angle will represent the phase lag. That is what it is. Okay. You just have to put s equals to j omega in the equation. Let's see. This is the first order process, Kp tau ps plus 1. The same as this, isn't it? We started with the first order process, Kp tau ps plus 1, isn't it? Now replace this s by j omega. So if I replace by s by j omega, what I'm going to get? I'm going to get Kp divided by j omega tau p plus 1. Correct? Yes or no? Now this iota is in the denominator. So what I have to do? I have to multiply and divide this entire equation by minus j omega tau p plus 1 so that I can get iota in the numerator. Do you all agree? Correct or not?
Yes.
So if I do that, what I'm going to get? I can multiply this entire term. So what I'm going to get? This Kp is multiplied to this first term. So that will be Kp divided by, here this denominator is going to be what? This j square omega tau p square minus j square omega tau p square plus 1, isn't it? So minus j square will become plus 1. So what we are going to get is tau p square omega square plus 1 in the denominator. And then numerator, I am going to have Kp into minus j omega tau p plus 1. So ultimately, after separating the term, what I'm going to get is Kp divided by tau p square omega square plus 1 minus Kp omega tau p iota divided by tau p square omega square plus 1. So now this is the real part and this is the imaginary part. If I wanted to find out the magnitude of g of j omega, what will be the magnitude of g of j omega? Magnitude of g of j omega is nothing but under root of square of the real term. Square of the real term will be what? Kp divided by tau p square omega square plus 1 whole square plus square of the imaginary term, which will be nothing but minus Kp omega tau p divided by tau p square omega square plus 1 and whole square. So this tau p square omega square plus 1, tau p square omega square plus 1, this is the common term, isn't it? Isn't it? And the square of that is there, isn't it? Correct? Do you all agree with me or not? So if I take the square of this particular term plus square of the second term, I can take this entire term common, isn't it? So what I'm going to get? In the numerator, I am going to get Kp square divided by this square plus second term will be Kp omega tau p is a divided by tau p square omega square plus 1, and this Kp term I can take it out. So that will be, this will be 1, and this minus of tau p omega square will be there, isn't it? So that 1 square term will get cancelled out here. Is it clear or not clear? Maybe I can derive for you. Just give me a minute. Is the derivation clear? How we are getting this Kp divided by uh, under root tau p square omega square plus 1? Are you all getting?
Yes, sir.
Yes, sir.
I I will derive. Just give me a minute. Give me a minute. Okay, let me just do the derivation here. Okay, so what I am going to get? This will be nothing but Kp divided by tau p square omega square plus 1 whole square, correct? And again the square of this entire term, but this minus sign will also going to become plus. So I am omitting that minus sign. So what we are going to get here? Kp omega tau p divided by tau p square omega square plus 1. And this entire term is square, correct? Now this Kp square is here, that this Kp square, and here also Kp square is there. So that Kp I can take it out. So Kp I have taken out, isn't it? Now what is the remaining term? What is the remaining term? 1 is here, isn't it? So 1 plus omega square tau p square, isn't it? So what I'm going to have? 1 plus omega square tau p square, and divided by I will have 1 plus omega square tau p square whole square, correct? Now this first term will get cancelled out with the square term. So what we are going to get is Kp divided by under root of 1 plus omega square tau p square. Do you all agree? Correct?
Yes, sir. Yes, sir.
So this is what we have obtained here. See, Kp divided by tau p square omega square plus 1. Is that clear to everyone? Hello?
Yes,
Sir,
sir.
sir,
Yes, sir.
Please tell me.
sir, can we put S equal to J omega in if the process is unstable?
If the process is unstable, then no. I will prove that. Why we are saying no. Okay. All right. This is only possible when the process is stable. Okay. Process is stable means the transfer function should be stable. Okay. That is what we are going to prove. All right. Is it clear to everyone? So you can see this is the amplitude ratio we have obtained directly. Yes or no? This is the amplitude ratio. See, the amplitude ratio is given by what? The amplitude ratio we have defined here is Kp divided by under root tau p square omega square plus 1. I have obtained directly this amplitude ratio just by putting S equals to j omega. That's it. Isn't it? Similarly, the phase angle is tan inverse of imaginary part of g of j omega divided by real part of g of j omega. Now, imaginary part of g of j omega is this minus Kp omega tau p divided by tau p square omega square plus 1, and this entire term divided by kp divided by tau p square omega square plus 1. So this denominator will get cancelled out with this denominator. Again, this kp will get cancelled out with this kp. So ultimately, the only term remaining will be minus omega tau p. Is it clear to everyone? So you can see that amplitude ratio and phase angle directly we can obtain by replacing s by j omega in the transfer function and then finding the magnitude and phase angle. So when we are finding the magnitude of g of j omega, this is equals to the amplitude ratio. And when I am finding the phase angle of g of j omega, that is nothing but phase lag directly. So you can see I don't need to do a detailed derivation like this. No need. I can directly get the phase angle and the amplitude ratio directly by putting s equals to j omega. Is it clear to everyone? Hello? Is it clear to everyone?
Yes, sir.
There is a reason why s equals to j omega. Okay. Here I have not proven it, but why s equals to j omega, there is a reason, and we can prove. Mathematically, we can prove why s should be replaced by j omega. Maybe I can give you a qualitative reasoning here. When we get a sustained sine wave, tell me, in a complex plane, when we get a sustained sine wave, anyone? Remember, we have said the stability. In the stability, how we find out the stability? Where the roots are located in the complex plane, isn't it? When the roots are located on the real
What
axis, on
side
the
of
left hand side of the imaginary axis, we get a stable response, but exponential response. When we have a roots which are imaginary and again located on the left hand side of the uh, uh, imaginary axis, in that case we get a response which is stable, and the sine wave is going to die out with time, isn't it? We get a sustained sine wave only when the roots are located exactly on the imaginary axis. Do you all agree? Yes or no?
Yes. Yes.
When the roots are located exactly on the imaginary axis, what will be the value? There is no real part. There is only a imaginary part. Imaginary part means these are represented by j omega, isn't it? Where omega is the value and j is actually representing the imaginary value, isn't it? Remember, this is what we have seen here. Let me take this example. Remember, in this particular case, we said this s equals to 1.28 j. Where this 1.28 j is located? Somewhere here, isn't it? So that means at these two locations, what is the value of s? At these two locations, what is the value of s? Tell me. What is the value of s? J omega. Exactly. Yes or no? Where omega is? Where omega is 1.28. Can you see why s is replaced by j omega? Because I am finding the roots exactly at the imaginary axis. Remember, here replacing s by j omega, there is a reason. It's not arbitrarily done. There is a reason. You can prove that. Is it clear to everyone? Hello?
No, sir.
Not clear? Okay.
Yes, sir.
Let me go. Okay. Remember, when we have these 2 points represent what? Tell me. This point and this point. This is what we have seen in root locus. What these 2 points represent? What will be
Imaginary
the
part
response
of
at
it.
these 2 points? When my
Sinusoidal.
roots are located on the imaginary axis, what type of response I get?
Sinusoidal.
Sinusoidal is there, but sustained sine wave we get. Here also we get a sinusoidal response. But then sine wave is not a sustained sine wave. That sinusoidal input is going to die out with time. Yes or no? I will have a response where sinusoidal response is going to die out with time. Only in this particular case, my response is not going to die out. It will be a sustained sine wave. I'll go back. Let me go back to a the figure which we have done earlier. Just give me a minute. Maybe then I will be able to give you a interesting. Ah, remember this is the figure we have seen earlier. Yes or no? Correct.
Yes, sir.
Now, what type of response we get when the roots are located here at the imaginary axis? What type of response we get? We get a sustained sine wave. See, this is the sustained sine wave.
Yes.
Sine wave is not dying out. Let's say I am having the roots here. In that case, the sine wave is dying out with time. I am getting a sustained sine wave only when my roots are located on the imaginary axis. Isn't it? Correct.
Yes.
Now what type of response I am getting here? This is what we are seeing. What type of response we are getting here? Tell me. Is the sine wave dying out here?
No, sir.
We are getting a sustained sine wave. That is what we have written here. See, my ultimate response is going to be a sinusoidal wave with the same frequency, and it is not dying out. It's a sustained sine wave I am getting. So when I am getting a sustained sine wave, what it means? What it means?
It means it is on the
It
imaginary
means
axis.
that the roots are located on the imaginary axis. That is what the meaning is. When I am getting the output, which is a sustained sine wave, its meaning is you are getting your roots exactly on the imaginary axis. And when you are having roots exactly at the imaginary axis, what is the value of the roots?
J
The
omega.
value of the roots is j omega. Can you see? Here omega is 1.28. You are getting s equals to plus or minus j omega. That's it. Correct?
Yes, sir.
Remember, that is what we are getting everywhere. Even in this particular case also, we are getting the same. In this case also here, what roots we are getting? See, what roots we are getting here? 3.32 iota
3.32.
and minus 3.32 iota. So we are getting a j omega, where omega is 3.32. Can you see the point? Whenever I am having the roots located on the imaginary axis, my roots are j omega directly. So now you can see whenever I am getting a sustained sine wave, replacing s by j omega, replacing this s by j omega is actually making sense. It's not arbitrarily done. There is a reason why we are replacing s by j omega, because this is the location where I'm going to get the sustained sine wave. And in this particular case, I'm getting a sustained sine wave, and therefore replacing s by j omega makes sense. It's not arbitrary. Is it clear to everyone?
Yes, sir. Clear.
I'm not able to, get that confidence from you. Is it clear to everyone? Your answers are not confident. Is it clear to everyone?
Yes.
Yes, sir.
So see,
Yes,
this
sir.
type of discussion you will not get in book at all. I am telling you, this type of discussion is not there in any of the book. That I can confidently say. Okay. All right. Let's move. Let's move. Now, okay. So what we have proven here is I can directly get the amplitude ratio and the phase angle just by replacing s by j omega, isn't it? And then we can find out the magnitude of j omega. That will give me the amplitude ratio directly, and the phase angle of j omega will be nothing but the phase lag. Okay. Now let's prove this particular thing in a generalized manner. Now, so far we have proven only for the first order system. Let's prove it for a general system. Okay, so let's say g of s is a transfer function of any system, isn't it? Which is given as qs by ps, isn't it? Where the roots of this p of s is going to give me the poles, yes or no? And for a timing, let's assume that this particular process is a stable process. So that means all the roots of P of S are located on the left hand side of the imaginary axis. Is that okay?
Yes, sir.
Yes, sir.
Now we wanted to prove a generalized results. What are the generalized results? Generalized results are this. These are the three generalized results. The ultimate response of the system to a sinusoidal input is also a sinusoidal wave. This is what we have to prove first. Second thing is the amplitude ratio. The amplitude ratio of the process should be equals to the modulus of G of S by substituting S by J omega. This is the second result we have to prove. And the third result is the phase angle of the process is given by the phase angle of G of J omega. This is what we have to prove on a generalized transfer function. So let's take a generalized transfer function G of S, which is given by QS by P of S, isn't it? So in this case, let's say the input F of S is input F of T is A sine omega T. So F of S will be A omega divided by S square plus omega square, isn't it? So if I multiply this F of S in this particular equation, so Y of S is given as G of S into A omega divided by S square plus omega square. Do you all agree? The G of S is any general transfer function of a stable process. Is that okay?
Yes, sir. Yes.
Now, in this particular case, okay, when I'm saying that this G of S is a transfer function of any process, it can be any nth order process. I can represent this G of S in terms of different poles, and I can separate their individual partial fractions like C1 divided by S minus P1 plus C2 divided by S minus P2, and that summation goes all the way to Cn divided by S minus Pn, where P1, P2, P3 all the way to Pn are the poles of the denominator P of S. Do you all agree?
Yes. Yes.
Now I am saying that this process, remember this entire bracket is actually coming from where? This is coming from G of S. Whereas this remaining two roots, these remaining two roots are actually coming from what? These are coming from the sinusoidal input. Do you all agree?
Yes.
Now let's say if I invert this entire equation into a time domain and uh, find out the response at t tends to infinity, what will be the contribution of this particular term? The contribution of this particular term will be C1 e raised to the power minus P1t e raised to the power P1t plus C2 e raised to the power P2t plus C3 e raised to the power P3t, and that summation goes all the way to Cn e raised to the power Pnt. Correct. And we are assuming that P1, P2, P3 all the way to Pn all are the negative numbers. Why? Because the system is stable. If the system is stable means what? All these poles are located on the left hand side of the imaginary axis. That means P1, P2, P3 all the way to Pn, all these poles are negative values. Do you all agree?
Yes. Yes.
So what will be e raised to the power P1t when t tends to infinity?
0.
Zero. So contribution of all these terms are going to be zero when t tends to infinity. Yes or no? Correct. So that's what is happening. When I'm looking at the output at uh, y at t tends to infinity, actually the contribution because of the process becomes zero. And the only contribution because of the input is there. And that is corresponding to the sinusoidal wave, sustained sine wave. Okay. So this is what we are proving here. See, this is the entire term. These two terms are coming from the input. So this bracketed terms are going to give me the terms like e raised to the power P1t, e raised to the power P2t, all the way to e raised to the power Pnt. And since P1, P2, Pn all have the negative real parts, when I am looking at the steady state value at t tends to infinity, all these terms are going to become zero. All these terms are going to become zero. So steady state value of y when t tends to infinity will be given by what? A into e raised to the power minus j omega t plus b into e raised to the power j omega t. Do you all agree? Because the contribution because of this process transfer function are going to become zero when t tends to infinity. So only contribution remaining will be from the sinusoidal input, and that is given here. Do you all agree?
Yes, sir.
Okay. So once we have represented this, now the only thing required is I wanted to find out these constants A and B. Remember here, these A and B are the constants. So I only need to find out the constants A and B. How I can find out A? Tell me. I can multiply this entire equation. I can multiply this entire equation. So remember, this entire equation is given by what? If I represent this, this is the entire equation. This is the entire equation, isn't it? I can multiply this entire equation by s plus j omega, isn't it? S plus j omega, and then put s equals to j omega. I will get directly A. So that s plus j omega will cancel out here, isn't it? So I will get g of s a omega divided by s minus j omega, and I can replace s by minus j omega. So that's what we are doing here. So if you do that, we will get directly A, and A comes out to be A into g of minus j omega divided by minus 2j. That is what we are going to get. Similarly, B will be obtained as A into g of j omega divided by 2j. That's it. Now this is also giving me another corollary of the same discussion we had just one slide before. Remember, I said why we are replacing s by j omega. Now you can see here also we are replacing s by j omega. Yes or no?
Yes, sir.
Can you see the point? Isn't it? So in this case, A will be given by A into g of j omega divided by minus 2j, and B will be given by A into g of j omega divided by 2j. This is similar to what we have seen in tutorial number 6. Exactly same. I am doing this entire analysis in terms of G. So see this entire term will be here equals to this term, isn't it? Now I can multiply this entire term by s plus j omega. So what will happen to the left hand side? In the left hand side, this s plus j omega will get cancelled out here, and here I will have only term associated with a when I put s equals to minus j omega, isn't it? So only term remaining here will be a. All other term will be multiplied by s plus j omega, and therefore that all the remaining terms are going to become zero, except a. So only a will be remaining here. So a will be given by g of minus j omega into a omega divided by, again this s will be replaced by minus j omega into minus j omega. So that becomes minus 2j omega. So that's what we are getting here. See, ag minus j omega divided by minus 2j. Okay, all right. Is that clear? Hello.
Yes, sir.
Similarly, b will be given as a into j of j omega divided by
Really.
2j. And now I can put this a and b in this equation, in this particular equation, and simplify. So a into g of j omega divided by minus 2j e raised to the power minus j omega t, plus a into g of j omega divided by 2j into e raised to the power j omega t. Again, this g of j omega and g of minus j omega and g of j omega, these two terms. See, g of j omega is what? This is the complex number. So I can represent g of minus j omega in terms of its magnitude and phase angle, isn't it? So g of minus j omega can be represented as magnitude of g of minus j omega into e raised to the power minus j phi. I am using the same property here, which is this, isn't it? Any complex function can be represented in terms of its magnitude and phase angle. So same property is used here. See, so g of minus j omega is given as g of minus j omega, magnitude of that into e raised to the power minus j phi. Now magnitude of g of minus j omega is actually same as g of j omega. Magnitude of g of j omega doesn't matter. So I can represent this as magnitude of g of j omega into e raised to the power minus j phi. Similarly, this g of j omega can be represented as magnitude g of j omega into e raised to the power j phi. And this again I am going to put in this original equation, and I can take this magnitude term common. If we take this magnitude term common here, what we left with is this a into g of j omega. We can take magnitude of g of j omega, we can take it common. So what we are left with is e raised to the power j omega t phi minus e raised to the power minus j omega t plus phi divided by 2j, and this entire term can be represented as sine omega t plus phi. So this is what the equation we are getting. Now if I compare this particular equation with the input, what was the input? What was the input? This is the output. Remember, this is the output. What is the input?
A sin omega t.
A sine omega t. So if I compare this input with this output, what is the amplitude ratio?
G
This is the
omega.
amplitude of the output, isn't it? A into magnitude of
G
g
of
of
G
j
omega.
omega. And the amplitude of the input is A. So what will be the amplitude ratio?
G of G omega
Directly
modulus.
magnitude of g of j omega. And phase angle phi. Phase angle phi is nothing but the phase angle between the imaginary part and the real part of g of j omega. So you can see that this result, this result is actually a generalized result for any transfer function g of s, provided that this transfer function should be corresponding to a stable system. Do you all agree? Yes or no?
Yes, sir.
So that is what we are concluding here. The last equation proves that we set out to prove that the ultimate response at as t tends to infinity is a sinusoidal input with a phase angle, sorry, when t tends to infinity, it's a sinusoidal input with a frequency omega, and the amplitude ratio is given as g of j omega. Similarly, the phase angle is given as the argument of g of j omega, isn't it? Now let's apply this entire analysis to different processes. Okay, so let's say if I am having a pure capacitive process, what is the transfer function of the pure capacitive process? The transfer function of the pure capacitive process is Kp by S. Let's replace this S by j omega. So that gives me Kp divided by j omega. And it is equals to, since this iota is in the denominator, we have to multiply it and divide by j omega. So what we are going to get? We are going to get Kp j omega divided by minus omega square, isn't it? Minus omega square. So this omega will cancel out with the omega which is in the denominator. So we are going to get minus j Kp divided by omega, isn't it? So this will have a real part 0 and the imaginary part is given as minus Kp by omega. Do you all agree? So what will be the amplitude ratio? Amplitude ratio will be magnitude of this g of j omega. So that is nothing but square of the real part plus square of the imaginary part. So square of the real part is 0. Square of the imaginary part will be Kp square by omega square and under root of that. So what we are going to get? Magnitude of g of j omega will be given as Kp by omega directly. And what will be the phase angle? Imaginary part by real part. Imaginary part is minus Kp by omega. Real part is 0, isn't it? So that is minus infinite. So tan inverse of minus infinite is minus 90. So you can see that whenever I am having a pure capacitive process, my amplitude ratio is Kp by omega, whereas my phase shift is minus 90 degree. Again, you can see this particular transfer function Kp by S. Where this S is located? What is the value of S here? What is the root of the denominator? 0. So when my roots are located at the origin, what is the process? Process is stable or unstable? Process is stable or unstable? Anyone? Hello?
Stable.
So you can see that this is the stable process, and we can clearly obtain the amplitude ratio directly replacing S by j omega. That gives me Kp by omega as the amplitude ratio, and the phase angle comes out to be minus 90. Okay. Now let's look at the n non-interacting capacities in series. So when I am having n non-interacting capacities in series, we are having G1s, G2s, GNs. So let's say all these individual capacities are the first order processes. So these are given by K1 divided by tau 1 s plus 1 into K2 divided by tau 2 s plus 1. And this multiplication continues all the way to Kn divided by tau n plus 1. Now in this particular case, again, if I replace S by j omega, what I'm going to get? G of j omega will be given as G1 of j omega, G2 of j omega, and multiplication continues all the way to Gn of j omega. Now, if we represent g of g1, j omega will be nothing but what? Magnitude of g1 j omega into e raised to the power minus j phi 1, isn't it? So for any ith capacity, we can write this as gi of j omega magnitude into e raised to the power minus j phi I, isn't it? Now in this particular case, all these magnitudes we can take it out. So all these magnitudes are multiplied. And what will happen to the phase angle? Minus j into summation of all the phase angle is going to take place. So what it means? So whenever there are multi-capacity processes are there, their magnitudes are, whenever I'm calculating the amplitude ratio, their individual amplitude ratios are multiplied. Isn't it? That's what we are getting. Remember here, magnitude of G1 J omega is nothing but the amplitude ratio of the first process. This is nothing but the amplitude ratio of the second process. This is nothing but the amplitude ratio of the nth process. So all these amplitude ratios are multiplied when I'm calculating the overall amplitude ratio. So overall amplitude ratio will be given as K1, K2 all the way to Kn divided by under root 1 plus tau 1 square W square into 1 plus tau 2 square W square and multiplication all the way to under root 1 plus tau n square W n square W square. Similarly, the phase angle phi will be additive here. You can see phase angle is phi 1 plus phi 2 all the way to phi n. So here the phase angles are added. So phi will be given as tan inverse of minus omega t tau 1 plus tan inverse of minus omega tau 2, and that summation goes all the way to tan inverse of minus omega tau n. Is it clear to everyone? Hello?
Yes, sir. Yes.
Now let's look at the second order system. So second order system, again, this particular derivation we have already done by using first principle in the tutorial number 6. Now we are going to do it directly replacing S by J omega. This is what the tutorial number 6 was. There is a second order system is given, and then we have found out the amplitude ratio and the phase angle directly for a sinusoidal input. Now in this case, we are going to find out the amplitude ratio and the phase angle directly by putting S equals to J omega. So this is the transfer function. G of S is given as Kp divided by tau square S square plus 2 zeta tau S plus 1. Again, I can replace S by J omega. So what I'm going to get? If I put S equals to J omega here, so S square will be J omega square, isn't it? So this J square will be minus 1. So what I'm going to get? I'm going to get minus tau square omega square. And this one here. So these two things I am combining here. So minus tau square omega square plus 1. And this 2 zeta tau S. Here S is replaced by J omega. So we get 2 J zeta tau omega. Now you can see that here the iota is there in the denominator. So whenever iota is in the denominator, we have to multiply and divide the terms so that we can eliminate the iota in the denominator. So that's why we are multiplying and dividing minus tau square omega square plus 1 minus 2 j zeta tau omega. If you do that, in the denominator, what we are going to get is 1 minus tau square omega square whole square plus 2 zeta tau omega square, isn't it? And in the numerator, this kp is multiplied to this entire term. So this kp multiplied by this first term is going to give me the real part. So kp into 1 minus tau square omega square divided by under root 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. This will give me a real part minus this iota I have taken out minus iota into 2 kp zeta tau omega divided by, again this common denominator 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. This particular term gives me the imaginary part. Now again we can find out the amplitude ratio. What is the amplitude ratio? Square of the real part plus square of the imaginary part and under root of that. So if you do that, we can directly get the amplitude ratio, which is nothing but g of j omega, which comes out to be kp divided by under root 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. This is what we are going to obtain if we square the real part plus square the imaginary part and add them and take the under root of the entire term. That will give me the amplitude ratio directly like this. Similarly, the phase shift or a phase angle will be what? Tan inverse of imaginary part. So this is the imaginary part divided by the real part. So this denominator, common denominator will get cancelled out. This kp will also get cancelled out. So what is remaining will be minus of zeta tau omega divided by 1 minus tau square omega square. That is what we are going to get. So phase angle in this case comes out to be tan inverse of minus 2 zeta tau omega divided by 1 minus tau square omega square. And again, the minus sign is there. So clearly this entire term is going to give me a phase lag. Okay. Is it clear up to this to everyone? Hello.
So here we are taking assumption that second order system is a stable process.
So second order system is always stable. Second order system is always stable. Remember we said second order system. Okay. Let me look at, okay, let's look at this particular problem. This will give you a second order system. So what will be the roots? Minus 1 by tau
Minus 1
1
by
and
tau.
minus 1 by tau 2.
Yes.
And tau 1, tau 2 are positive. So
Yes,
that
sir.
means your roots are
Yes,
always
negative.
located on the left hand side of the imaginary axis. In fact, we will prove. First order system and second order system are always stable. As we go ahead in the frequency response, we can actually prove that the first order system and the second order system are always stable. Third
Yes.
order system can be unstable. Okay, we will prove that. All right.
Yes.
Is that clear?
Yes.
Now let's look at the date time. Let's look at the date time. Date time, what will the transfer function of the date time? E raised to the power minus TDS. E raised to the power minus TDS. That is what the date time is. Now, this particular equation I can compare with the standard equation. What is the standard equation? When I am having g of s as a complex function, I can represent it in terms of the amplitude ratio and into e raised to the power j phi, where you can see that the amplitude ratio directly comes out to be 1 and the phase angle phi will come out as minus TD omega, because this s will be replaced by j omega, isn't it? So TD omega will be minus TD omega will be the phase angle. Now, this is a very, very interesting equation. Why? Because this simple analysis of the phase angle here by replacing this date time here by representing this S by J omega is actually giving me the amplitude ratio equals to 1 and the phase angle of minus TD omega. And combining this amplitude ratio and the phase angle in this entire equation is easy. And this is the reason why you don't require a simplification of the exponential term when you are using a frequency response. When you are using a frequency response, you don't need to simplify this exponential term at all. You can directly represent this exponential term in the equations of the amplitude ratio and phase angle without simplifying. Okay. I will again prove why this particular equation is important. I will prove as we go ahead. In fact, half of the answer, remember I said in the starting of the class, why frequency response? Because it enables solving the feedback control system even with the date time without approximating it. You don't require the approximation of the date time when you are doing the frequency response. So even though the route stability criteria or root locus can give you the stability of the control system, but whenever there is a exponential terms, whenever there is a date time associated with the system, you have to simplify this date time using a Paird's approximation. But such approximation is not required when you are finding the stability by using frequency response. So slowly we are building the concept. We are going to even build the concept of stability by using frequency response as we go ahead. Now we are only building the concepts. We have not even gone to the stability. Okay. Is it clear to everyone? So whenever I am having a date time, the date time has a amplitude ratio equals to 1 and the phase angle minus TD omega. Okay. Is it clear to everyone?
Yes, sir.
Okay. Now let's look at the controllers. Let's look at the controllers. So now, if you are having a proportional controller, what is the transfer function of the proportional controller? Just Kc. Just Kc. There is no S term here. So I cannot replace S by J omega here. Even if I replace S by J omega here on the left hand side, there is no S term on the right hand side. So we get just Kc. Kc is a real term, real number. There is no imaginary number here. So what will be the amplitude ratio? Just Kc, isn't it? Remember what is amplitude ratio? Under root of square of real part plus square of imaginary part. There is no imaginary part here. So square of the real part is nothing but Kc square and under root of that will be just Kc. So amplitude ratio comes out to be just Kc directly. Whereas phase angle is nothing but what? tan inverse of imaginary part by real part. What is the imaginary part here? 0. 0 by Kc is 0. So tan inverse of 0 is 0. That's why phase angle you are getting 0. Is it clear to everyone?
Yes, sir.
Now look at proportional integral controller, PI controller. PI controller has a transfer function Kc given as 1 plus 1 upon tau is. Now there is a S term here. I can replace this S by j omega. So this S will also get replaced by j omega. What I'm going to get? Kc 1 plus 1 upon tau I into j omega. Now here iota is in the denominator. So what we have to do? What we have to do when iota is there in the denominator? We have to
Rationalized.
multiply and divide by a term, isn't it? So tau I, j omega is there here, isn't it? So we have to multiply and divide by j omega term. So what we are going to get? What we are going to get? 1 minus if I multiply and divide by j omega, 1 minus j into omega divided by what we will get. So here in the denominator, we are going to get a term omega tau I directly. Yes or no? Minus j divided by omega tau I, isn't it? That is what the term I'm going to get. Yes or no?
Yes, sir. Yes.
Maybe I can do that. Just wait. Maybe I can do that. So I am able to do it. So I can replace s by j omega. So you will get Kc 1 plus 1 upon j omega into tau I. Now this entire term we can multiply by minus j omega divided by minus j omega here. So we will get Kc 1 minus this j omega that becomes uh, uh, this minus and minus is there, so that will become minus j square omega square. So that minus of j square will be -1, so plus we are going to get, but this minus sign is there and this omega square is there, but numerator I am having the omega, so that omega will get cancelled out. So what we are going to have is j divided by tau I into omega. This is what the term I'm going to get, isn't it? Now, here the real part is 1, imaginary part is -1 by tau I omega. So what will be the square of the real part? Real part will be 1 plus imaginary part square will be 1 upon tau I omega square, isn't it? And under root of this entire term is going to be amplitude. So that is what into this Kc will come out. So that is what we have written, amplitude ratio. Is it clear? Is it clear?
Yes, sir.
And phase angle will be imaginary part by real part. So this is the imaginary part. So -1 upon tau I omega divided by a real part which is 1. So minus of tan inverse of minus of 1 upon omega tau I, that will be the phase angle directly. Correct? Similarly, if let's say we are having proportional derivative controller, this is the controller, proportional derivative controller. So in this particular case, if I replace this s by j omega, I am going to get the amplitude ratio, which comes out to be Kc under root 1 plus tau d square omega square. That is what I'm going to get. And the phase angle comes out to be tan inverse of tau d omega. Now this is a very interesting thing. Okay, this is a very interesting argument here. Remember here what we have obtained, phase angle phi comes out to be tan inverse of minus of this term. And that's why we are going to get a phase lag here. Correct? You can see this is the tan inverse of minus term. So we are going to get a phase lag. But what about proportional derivative controller? What is the tan inverse of TD omega? There is no minus sign here. There is no minus sign here. So what we can conclude here? Whenever we have a derivative controller, instead of getting a phase lag, we are getting actually a phase lead. we are getting a phase lead here. There's no minus sign here. So you can see, remember what happens in the derivative controller. Derivative controller actually anticipates the future error. That's why we are getting a phase lead here. Can you see the point? Derivative controller actually does what? It actually predicts the future error, isn't it? So that's why we are getting a phase lead here. Now let's look at the proportional integral and derivative controller. So proportional integral and derivative controller, this is the transfer function I am having, kc 1 plus 1 upon tau is plus tau ds. Here again we can replace s by j omega. If I replace s by j omega, then the amplitude ratio comes out to be kc under root in the bracket td omega minus 1 by tau I omega whole square plus 1. So see, this is the plus. This particular term td omega will be plus for the uh, derivative controller and minus for the integral controller. So that's why this term comes out to be td omega minus 1 by tau I omega whole square plus 1. Again, here in this case, the phase angle comes out to be tan inverse of td omega, tan inverse of td omega minus 1 by omega tau I. So here you can see that when I'm having the PID controller, I can have phase lag or phase lead both, depending on what is the value of TD and tau I. What is the value of tau D and tau I? Depending on that, I can get phase lag or phase lead. Okay. Is that clear to everyone? Hello?
Yes, sir. Yes, sir.
Okay. So now what is the time? I think it is 8:40. I will only explain this Bode diagram and we will stop. Again, hello?
5G unlimited or
क्या हो गया भाई? 5G का किसको डिस्कशन कर रहे हैं?
शुभम
somebody is discussing 5G. Okay, so let me give you a description of the Bode diagram and then we will stop. I will not take more than 5 minutes. Remember, I have promised that we will continue this class only up to 8:45. Okay. Okay, so what is Bode diagram? Bode diagram is a very important. Remember, so far we have only looked at if there is a sinusoidal input given to the first order process, second order process, pure capacitive process, date time, proportional controller, PI controller, PID controller, what type of amplitude ratio and the phase angle we are expected to get. That is what we have found out. Correct. Remember, I said the frequency response is used for what? It is used for stability. What was the need of frequency response? You can find out the stability of the control system involving the date time without approximating the date time only by using frequency response. So ultimately our aim is to understand the stability by using frequency response. But we have not said anything about the stability so far. Okay. So this is what we are trying to understand now. Stability actually, the important part in the stability of the control system using frequency response is a Bode diagram. Bode diagram is named after the scientist Bode. Okay, what is Bode diagram? So Bode diagram actually gives you a, it's a convenient way to represent a frequency response characteristic of a system. In this particular case, in a Bode diagram, there are two types of plots. One is we are plotting amplitude ratio versus frequency. That is plot number 1. And again, we are plotting the phase angle versus frequency. So both these plots we are plotting. And then we are trying to find out the stability of the control system based on these two plots. There is something called as a Bode stability criteria, which we will again look at in detail as we go ahead. So Bode diagram constitutes a convenient way to represent the frequency response characteristics of a system. The amplitude ratio and the phase angle of the ultimate response is obtained with respect to the frequency omega. Okay, it has two plots. The first plot is amplitude ratio versus frequency, and the second plot is phase angle versus frequency. These are the two plots we are looking at. Now let's look at the first order process. So first order process amplitude ratio is given as Kp divided by under root 1 plus tau p square omega square. So remember, in this case, the omega is varying from 0 to infinity. I wanted to represent how my amplitude ratio is varying with respect to frequency omega, and frequency is varying from 0 to infinity. So in order to represent the results in a given plot, we actually plot this amplitude ratio and the frequency in a log scale. Why in log scale? So that we can able to represent the frequency value from 0 to infinity. That is the reason. Okay. So typically the log plot is used for representing AR versus omega, and a semi-log plot is used to represent the phase angle versus omega. Okay. So let's look at the first order system. So first order system amplitude ratio is given as Kp divided by under root 1 plus tau p square omega square, and the phase angle is given by tan inverse of minus tau p omega. Now here AR, I can find out AR by Kp and I can take a log of that. If I take a log of AR by Kp, what I'm going to get? I'm going to get minus 1 by 2 log of, remember in this case, the log to the base 10 is there. Okay. So I can take log of AR by Kp equals to minus 1 by 2 log 1 plus tau p square omega square. Here we have taken a log. We have not taken a ln. It's not a natural log. This is a log to a base 10. Please note that here this log is a log to the base 10, not to a base. It's not a natural log. Okay. So log AR by Kp comes out to be minus 1 by 2 log 1 plus tau p square omega square. Now, in this case, since the tau p is constant and only thing which is varying is omega, but for a convenience, we are taking tau p and omega as one variable. So we are looking at how tau p and omega is varying from 0 to infinity. Okay, because tau p is anyway constant. So when omega is 0, tau p omega is actually 0. And when omega is infinity, tau p omega is also infinity. So let's find out what values we are going to get for log AR by Kp when omega tends to 0 and omega tends to infinity. So when we are finding out how log AR by Kp is going to vary when omega tends to 0, that is referred as low frequency asymptote. And when we are finding out how log AR by Kp is going to vary with omega when omega tends to infinity, then this is referred as high frequency asymptote. So in this case, when omega tends to 0, this particular term is going to become very, very small, very equivalent to 0. In that case, what I'm going to get? Minus 1 by 2 log of 1. Log of 1 is what? 0. Isn't it? Log of 1 is 0. So AR by Kp will be what? Log of a particular term is 0 when AR by Kp is equals to 1. So you can see log of AR by Kp is equals to 0. That means AR by Kp should be 1. So this is something referred as low frequency asymptote. And when omega tends to infinity, this particular term is dominating over 1. So we can have this 1 we can neglect because tau p square omega square is very much large compared to 1. In that case, I am having log of tau p square omega square. So this 2 can come out here. So 1 by 2 will get cancelled out with 2. So what I'm going to get? Minus log of tau p omega. So now if I look at this particular equation, what it means? If I plot log AR by Kp versus tau p omega, it will have a slope of minus 1. That's what it means. Again, this is the low frequency asymptote, whereas this is the high frequency asymptote. And this change of low frequency to high frequency takes place when this 1 is equals to tau p square omega square. So when 1 is equals to tau p square omega square, that means omega should be equals to 1 by tau p. And this particular value is called as a corner frequency. There are at least 3 types of frequencies: corner frequency, crossover frequency, resonant frequency, etc. Okay, all these frequencies have a different meaning, and we are going to look at these little bit in more detail in the next class. So you can see that if I plot AR by Kp in a log plot versus frequency, you get a low frequency asymptote where AR by Kp equals to 1, and in a high frequency asymptote, the slope comes out to be minus 1. So this is the high frequency asymptote. This is the low frequency asymptote. Again, similarly, we can plot a phase angle. So phase angle starts from 0 and it goes to minus 90 when I am having a first order process. We are going to look at these details little bit in more uh, uh, detailed manner in the next class. So we will stop here unless you have any questions. Hello? Hello?
Sir, frequency response and whatever we covered today will not be a part of quiz.
No,
Right?
it will be a part of examination. The only thing is whatever we will cover up to frequency response, after that, that will not be a part of the examination. Remember, I said there are several topics like feed forward control. There is a topics like control system with multiple loops. There are the topics like this, what we call it as a uh, uh, inferential control or adaptive control. This will not be a part of your examination. I will probably cover that in the next week. Frequency response, most likely we will cover by this Friday. Okay, so that will be the syllabus of your examination. Is that clear? Frequency response
Yes,
will
sir.
be a part of examination. Please note that. Whatever we will cover after the frequency response will not be a part of your examination.
Sir,
Is that clear?
frequency response is part of
Hello?
कोई कोई part है क्या ये?
Akshay, is there any question?
No, sir.
Akshay Raj, is
No,
there
sir.
any question? So you are discussing with your friends. That's why I'm asking. Please
The
note that the
frequency
frequency response will be a part of your examination.
sir,
Frequency
of quiz or
response and how to design the controllers using frequency response. That is definitely a part of your examination. But the higher uh, the topics of advanced process control like feed forward control, inferential control, control system with multiple loops, control system with large date time. These are the topics we will not have in the examination. Probably I will cover in the next week some of these. Okay, because these are already there in your gate syllabus, but those will not be part
sir,
of your examination. But frequency response and designing the controller using frequency response will definitely be a part of your examination. Both this examination, quiz 2, as well as your end term examination. Is that clear to everyone?
Sir, exam means major or quiz, sir?
Both examinations. So quiz is on this Sunday, and your major examination will be whatever the schedule is there. Okay.
The frequency response will be part of quiz or not, sir?
It will be a part of quiz. Whatever we will cover
Okay.
by Friday will be a part of your quiz.
Okay.
So there are 2 more tutorials we have to cover on frequency response that we will cover probably in the next week. Okay. There are 2 tutorials, tutorial number 12 and tutorial number 13. So one tutorial is on Bode plot. Another tutorial is on designing the controller using frequency response. Remember, I said the frequency response is actually for finding the stability. We have not gone there so far. We are only looking at the concepts. We are not gone there. Okay, most likely tomorrow's class we will touch upon that particular thing, and Friday probably will complete. Okay, is that clear? Hello. So let me
yes,
download the attendance, and then we will wind up. Let me download the attendance. Download the attendance list. Okay. All right. Most likely, I will award the attendance to all the students. Most likely. Okay. Let me just go through the attendance whether the people have attended. Hmm. All right. Okay. So I'm extremely sorry for taking this 2 hour, but anyway, I have promised that these 2 classes are actually the classes which we missed in the Diwali week, isn't it? Based on your request. So definitely we wanted to make up those. Uh, so then we will have a class tomorrow, and we will have another class on Friday. Most likely we will cover the entire syllabus for your examination by Friday, and whatever the advanced topics are there, those probably we will cover in the next week. Is that okay? Hello.
yes,
Yes,
sir.
sir.
Okay.
So please go through the material. There are remaining 50 slides. I will put those remaining 50 slides on Scoop tomorrow. Okay, I'm sorry. I have put the slides up to 200. So 200 to 250, those slides I'm going to put on the Scoop tomorrow. Okay, all right. Okay, so let's stop here and see you tomorrow.
Thank you, sir.
Thank you everyone for joining.
Thank you, sir.
Okay,
Thank you,
all
sir.
right.